Now we want to use calculus to find the uncertainty in a function of several variables. Here I have written g equals f of x, y, and z. X, y, and z are something that we've measured, and so they have uncertainties. We could have more variables or go down to 2. The rule says that the uncertainty in g is equal to the uncertainty in the variable x times the partial derivative of f with respect to x, all squared, plus the uncertainty in the second variable, which is y, times the partial derivative of f with respect to y, again, all squared, plus, finally, the uncertainty in the third variable z times the partial derivative of f with respect to z, again, all squared, and then we take the square root. Now, the partial derivative is just like the absolute, or the normal derivative. The only difference is that when you use a partial derivative, you treat the other variables as if they're constants. We're going to do a couple of problems to show you how this all works out. Here's my first function. It's g equals x plus y minus z. So we have three variables, x, y, and z. We have to take the partial derivative of g with respect to all three. So partial of g with respect to x, that's just 1. The partial of g with respect to y is also 1. And the partial derivative of g with respect to z is -1. So those derivatives were easy to do. Remember, when we do the partial, it's like taking the regular derivative, except the other variables are treated like they were just numbers 5 or 7. Okay, so then the uncertainty in g is equal to the uncertainty in the first variable, delta x, times the derivative, which is 1. We square this, plus we take the derivative, the uncertainty in y times the derivative 1, squared again, plus the uncertainty in z times the derivative squared, all square root. And this is the same as delta x squared plus delta y squared plus delta z squared. This is exactly the same formula we used in 1101 and 1120. Okay, here's the second function. G is equal to x, y over z. X, y, and z are all variables. Again, we have three variables, so we do three partial derivatives. They are the derivative of g with respect to x, which is just y over z. The partial derivative of g with respect to y, which is just x over z. And the partial derivative of g with respect to z, which is going to be negative xy over z squared. Now we can write down the uncertainty in g. It's going to be delta x times y over z, all squared, plus the uncertainty in y, so delta y times the derivative, which is x over z, all squared, plus the uncertainty in z times xy over z squared, all squared. Take the square root. Perfect. Now that's a little messy, and we can make it a little neater. For instance, I can write this as delta x over x times xy over z squared plus delta y over y xy over z all squared plus delta z over z xy over z all squared. And xy over z is a common factor, and it's the same as g. So this is g square root delta x over x squared plus delta y over y squared plus delta z over z squared. That's the same rule for multiplication and division that we used in 1120 and 1101 labs. You don't have to do the simplification if you don't need to or you don't see something obvious to do. It doesn't make any difference in a spreadsheet how you calculate the numbers. Okay, here's my last function. G equals a e to the x squared. A and x are both measured variables, so they have uncertainties. So I'm going to have to take the derivative of g with respect to a. That's pretty easy. It's just e to the x squared. To take the derivative of g with respect to x, our second variable, I'm going to have to remember to do the chain rule. So this is going to be a e to the x squared. The derivative of e is its own derivative, times the derivative of x squared, which is 2x. So delta g is going to equal delta x e to the x squared plus, oh, sorry, I did that wrong, right? This term over here should be delta a. This is delta x a e to the x squared 2x squared. Take the square root. Again, we could simplify this a bit. We could take a e to the x squared outside, and this would then be delta a over a squared plus 2x delta x squared, which is a little easier to write down, or g root delta a over a squared plus 2x delta x squared. That's it. So as long as we understand the difference between partial derivatives and straight derivatives, all the calculus involved is fairly straightforward. On a spreadsheet, you want to do it piece by piece. We don't necessarily need to end up with a nice little formula to work with, right? Because we can do the different derivatives, calculate them in the spreadsheet, and have the spreadsheet do all the work for us. Bye for now.